Hello everyone. Now that we know how to fit different kinds of distributions to a particular data by using fit distribution plus package, and within that using the function like fitdist. So we have looked at how we can use the fit distribution package, fit distribution plus package, and within that using the fitdist function to fit some kind of distribution to a data. So we have tried fitting a gamma distribution to a particular data, or I may think of fitting a normal distribution to a particular data, right? So now that we know how to fit a distribution to a given data, and based on that get an estimate of the parameters of that distribution. If I am fitting a normal distribution, I can get mu and sigma. If I am fitting a gamma distribution, I can get a shape parameter and a rate parameter. So the most appropriate distribution with each of these parameters is typically provided by this fitdist function. Now we also have checked out what is the way I can compare between the distributions also. So some of the methods which we have looked at is log likelihood. So whichever is the method that is giving me a very high value for the log likelihood, that would be the most preferred kind of distribution. Similarly, we have looked at Akaike information criteria, which is like a measure of error, or even Bayesian information criteria, which is also a slightly different form of error. So wherein we want this particular error to be as less as possible if I have to choose a particular model. So these are some of the methods that we have already discussed when we are fitting the data to a particular distribution, right? So what I really want to look at here is, in some cases I can fit the data to a very general kind of a distribution, very normal one like a gamma or a Pareto or Weibull, something which is already known. Or in some cases I can even think of fitting a mixture distribution. Means there is some probability that it is let's say a gamma distribution, and there is some other probability that it is a Pareto distribution. So we can even fit those kind of models to the data. So whatever is the model that we are fitting, we have to really assess which model is an appropriate fit to our data. So apart from these mechanisms of log likelihood, AIC and BIC, here in this session we are going to look at various other methods through which we can measure which model is more and more adequate to this particular data set. What is the adequacy of the model that we have chosen for this particular data set? So there are different kinds of mechanisms that we have, right? So we can try out different kinds of mechanisms, different ways in which we have fitted the data, and then try out which one is more and more adequate for our data. So let's go ahead with it. Some of the mechanisms that are readily available for us to do the process. The first one is a histogram of the models that we have fitted, right? We have a histogram along with the empirical densities. So I can get the histogram plotted along with the empirical densities for the same. So empirical density is more coming from your actual data, histogram is coming from the fitted model. So fitted versus the actuals, we are trying to look at that. Similarly, the other option is, instead of looking at the densities, we can look at the distribution function plots, So we can look at the distribution function of the actual versus the fitted and see what is the level of fitment or the deviation. Then we can also look at the QQ plot and the PP plot, which are again other ways of really coming out with whether my data is more and more appropriately fitting to a particular distribution or not. And then we have real statistical tests which assess the goodness of fit. Right, earlier we have even looked at the CVM mechanism. Right, these are the various assessments of the goodness of fit, apart from Akaike information criteria as well as the Bayesian information criteria. So we will have a quick discussion about them. And finally, we also have the skewness kurtosis graph, which simply which represents what is the level of adequacy of a particular model to a particular data set. So all these things we will try out with the one single example that we have used earlier, right? So let's go ahead. First thing is histogram. We know how to plot a histogram. The observed data are divided into k classes, k different groups. Generally, we would prefer k to be more and more in line with the proportional to log n. So depending on what is the size of my data, I would prefer those many classes to be there as a part of my data. Again, though it's not a hard and fast rule, this is just a kind of a ballpark kind of a picture. So the number of observations in each class I am computing, which is what we are calling as a frequencies, and accordingly the rectangles are drawn. So we have a direct formula called hist, which is taking care of plotting of the histogram for any data set. So we are going with an estimator of empirical density. When we are talking of histogram, it's a kind of an estimator of empirical density, wherein the area of each rectangle is typically proportionate to the probability of occurrence of that particular area in that interval. So first thing, we will first plot, we will first fit a model, right? Let's try out 2-3 models on our data, which we have earlier done. So I am taking this cost variable itself, cost data set that we have used earlier for fitting the models. Just as a quick revision to what this actually contained, I am doing a simple head. So it contains X, date and ultimate cost. I am only taking the ultimate cost here for our workout purpose, right? So let me take this a small variable X, a small letter X, which I am taking as cost dollar ultimate cost. So I am taking only this ultimate cost column from here, and all other things I am ignoring. So this is the one that I have. Based on this ultimate cost, we will fit different kinds of distributions. So we'll try out 3 different distributions, right? All of them will go with maximum likelihood approach itself. So let's first fit a normal distribution. Normal distribution, I am calling it as NOR. So this NOR for me, first let me take this X as let me simplify it. Instead of having that big numbers out here, let me reduce them in terms of million. So let me divide it by 1 million. Okay, so if I look at the summary of X, so these are small numbers to work with, fair enough. So now let me fit a normal distribution to this data, right? So I'm calling it as, I need to load this library fit distribution plus. If it is not there, please install it, because we already have it. I'm simply loading it. Fit distribution plus is the package that we have loaded. Now within that, let me call normal as a variable, which is using the fitDist function. Just to recollect, fitDist function actually uses the name of the variable, which is x, the name of the data, which is x. Then I have to give the distribution to it. The distribution, I'm calling it as normal distribution here. And the method, by default it will take MLE, so I don't need to give it also, going with the maximum likelihood estimation approach. So this is what is coming out as normal. Okay, the D norm, okay, norm, I'm sorry, it's not normal, it is norm, because the D norm is defined, D normal is not defined. Okay, so I have a normal distribution model. So I can get the parameters of this model by typing in NOR. So the mean of this model is 1.015 and standard deviation is 1.067. Alright, let me consider. First thing, for a normal distribution here, I'll not talk about the other aspects here. The mean is 1.015 and the standard deviation is coming out to 0.6799. So probably 0.68. Let me round it up. So this is what is the best fitting normal distribution to this data. Similarly, let me take GAM, which is a gamma distribution, right? Or now I could also see the summary, which would give me the AIC and the BIC as well. So this gives me a log likelihood of minus 472. This is the log likelihood. Then this is also giving me AIC of 948 and it is giving me a BIC of 956. This is what is the story of normal. So similarly, let me do a gamma distribution, fit test. Again for this X, the distribution I am now calling it as a gamma distribution and the method is MLE itself. We know that we can use any of the four methods, MLE, MQE, QME, MME, method of moments, QME, method of quantiles, and goodness of maximizing the goodness of it, MGE. So here I am going only with the MLE because here I want to compare the model. So I am using GAM as a variable to hold the gamma distributed fitted value. So if I am taking the summary of this GAM, it is telling me the gamma distribution, right? Let me take the values. The gamma distribution here is having a shape parameter of 2.399. This is the shape parameter and the rate parameter is 2.362. This is how this gamma, the best possible gamma distribution has come out using the maximum likelihood estimator approach. The log likelihood is minus 385, much higher than normal. AIC is 774, much lower than normal, and BIC is 782. So this is what is the story associated with a gamma distribution. Let me take one more, which is a Weibull distribution, an extreme value distribution. So I'll take it as Weibull. Let me take fitdist X Weibull and method is MLE. Okay, so if I am taking the summary of Y, so here this is taking the shape parameter is 1.595. .595 is the shape parameter. Scale parameter is 1.133. These are the parameters of the Weibull distribution. And it says that the log likelihood is minus 391, slightly lesser compared to a gamma distribution. AIC is 786, slightly higher compared to a gamma, and BIC is 794, which is also slightly higher compared to a gamma. So if I say I am looking at between these three, it looks like gamma is more and more appropriate for this particular kind of a data, most appropriate distribution for this kind of a data. But now let's try out, right? I want to try out fitting using all the different methods to typically assess which one is more appropriate for our data. So I want to compare these three methods. So we got fittest objects. So we got three different objects which are the fittest objects for us. I can typically go for plotting all their densities. So I can use this function called densecomp. Let's see what is this densecomp function. So it is doing, it's again a part of the different plots. We have a CDF comp, densecomp, QQ comp, PP comp. So plots the empirical cumulative distribution. So if I am going with empirical data, CDF comp will plot empirical cumulative distribution against the fitted distribution functions. Densecomp plots the histogram against the fitted density function. So I can have fitted density functions, and I can even plot the actual values, wherein I could clearly see the histogram versus the different fitted values. So you see here the input that we are giving, densecomp. The first one is FT, fit distribution object, or a list of objects of the class fit distribution. So I can very well give a list of objects. So let me start giving the input here, right? I'll go with densecomp. I'll give a list because I want to look at all three of them. So I'll take a list. My first one is a normal distribution fit dist object. So I'll call it as NOR. That is my normal distribution fit dist object. Then I also have a gamma distribution fit dist object, which is the GAM. And I also have Weibel, which is again a Weibel distribution fit dist object. So this is my first input. Then I have to give the X limits and the Y limits. Okay, so let me not do anything on that. Let it typically take the default ones itself, the X limits versus the Y limits. If I have any kind of then probabilities, yes, by default the probabilities are true, so I don't need to really make any kind of a change. Main is giving me the right histogram and the fitted distributions. Let me call that as the name, histogram versus fitted distributions. So let me take that as the name. That is why I am calling main. If I want to give anything as x-axis labels, y-axis labels, these are very common stuff. I don't want to get into all these things. Right? Okay, line types and all these stuff. Colors, the fitment colors. If I want different colors for each fit, I can very well add. Okay, add legend. I can very well set by default the legend is true. So I don't need to specify unless I want to hide the legend. I can very well go ahead with the add legend true. But legend text is something which is better to define. So let's define the legend text. Right, let's define the legend text, which I can very well set it as, probably because we have three of them, let's call it as normal, the first one. The second one, let me call it as gamma distribution, and the third one, let me call Weibull. So I'll take the legend text as well. I think that should be sufficient for us. By default, the legend gets plotted in the top right. Let's leave all of them to the default itself. Right? So this is how the dense comp function is typically getting created for us. Okay, so you could see a difference now. These are the three plots. The red one is indicating a normal distribution. This is how the normal distribution data is coming out. And then the green is a gamma distribution, and the blue one is a Weibull distribution. So this is how the actuals are typically being plotted against the fitted distributions. You could clearly see out of these three options that are there in front of us, the green is looking more and more a decent representative of the overall histogram that got plotted, right? So the green is more or less representing on a similar note. So this is where we could say that the gamma distribution is more and more appropriately fitting this data compared to any other. So the dense comp as a function, it will allow us to fit the actual data against the entire fitted distribution. So I have to give only a list of fitted distributions as the input. So this is where it takes fittest objects only, and the fittest in turn has taken the actual data. So this is where the actual data got plotted in the form of a histogram, and the fitted models are plotted in the form of lines, which are telling me which distribution is more appropriately getting fit to this particular data set. And going with this, it looks like the histogram is more and more appropriately fitting to this particular data. So that's the first thing for us to understand. We can really evaluate the fitted model using the histogram versus the empirical densities, going ahead with a function called dense comp. Dense comp is a function which is plotting both the fitted values along with the actual values. So in some cases I may have my own mixture distributions also. Probably let me try that. Let me create one mixture distribution as well. So I would say the mixture distribution that I am looking at is a mixture of gamma and Pareto. Right? Let's say I want to look at a distribution which is a mixture of gamma and Pareto. So what is that? We'll say gamma distribution is having two parameters, right? So let's assume that they are A and B. So I'll use the d gamma function to get the densities of X with parameters A and B, and d Pareto as another function on X with parameters C and D. There is some probability P that the data belongs to a gamma distribution, and the 1 minus P that the data belongs to a Pareto distribution. So this is how we can create our own mixture distribution as well. So let me create one mixture distribution. So I'll call it as gamma Pareto. Right? Let me give a name to it, gamma Pareto. So we'll define a d function for it, d gamma Pareto. The d function is the density function, wherein I'm creating a new function x, and along with the x is the data. We are creating one which is the probability as the input to it, and four different parameters to it. A B belongs to the gamma function, a gamma distribution, and C D belongs to the Pareto distribution. So let's say this is the mixture that we are creating. So here we are saying the mixture is created like this. There is a probability multiplication multiplied with the d gamma. The d gamma is based on x, a, b, and 1 minus probability that we are multiplying it with the density function of Pareto. D Pareto x comma c comma d. So this is the function that we have defined, which is a mixture distribution. So there is a probability p that it is following a gamma distribution, probability 1 minus p that it is following a Pareto distribution. Similarly, I can also have a p function for it. Let me call it p gamma Pareto, which is again going with the same. We will give it as a function of, here forget again the same x, the prob a comma b comma c comma d, and the way we are computing it is prob multiplied by, I will do it as p gamma times x comma a comma b plus 1 minus prob times d p Pareto of x comma c comma d. So this is a p function for it. So we have created a mixture distribution, right? Now I really want to test whether this mixture distribution is, so let's call GAM pair. We are fitting a model for our data x using GAM pair. We are saying fit dist x. The name of the distribution is gamma Pareto. That's the name of the distribution that I want to fit. That is the distribution that we have created, a mixture distribution, which is a mixture of Pareto and gamma. So that's a distribution that we have created. It's not existing by default in the package. So we have created a mixture distribution. We want to fit this data x against this mixture distribution, again using the maximum likelihood approach itself. Let's see if we can fit it. Okay, the distribution name, we cannot create our own fitted distributions here. So we may have to give, okay, error in the start. Let me try if I should give any starting value for this, right? Instead of saying, so here, let me give some starting values of the parameters. So I think for a new distribution that we are creating, it might require the starting values. So let me take it as a less. The probability, let me take it as 0.5, 50% that it could be gamma, 50% it could be Pareto, right? And after that, let me give all the parameters. So let me say a equal to 1, b equal to 1, c equal to 1. Let me start with something, d equal to 1. So this is a list of initial parameters, let me give, and the lower values should be equal to 0. Some kind of initial startup, let me give. Let's see whether it, now it looks like it has taken the model. Yes, it has fitted. So it's basically like if we are creating our own mixture distribution, we should give some starting point for it to consider all the parameters. So some starting values of the parameters we have to typically give to it. So let me even add into the dense comp. I will also add, or if I take the summary first of all for this GAM pair, what is the coming out? Now you could see the log likelihood is minus 363. Wow, I have improved. The log likelihood is minus 363, I'm going with gamma Pareto kind of a combination, which is having a probability of 11.62 that it is a gamma distribution. A value is 0.97 for the gamma. B is 2.02, which is the rate parameter. And the shape parameter for Pareto is 117. And the scale parameter for Pareto is 50.23. So this is what the gamma Pareto distribution that it has fitted. This has come to minus 363. AIC is 737, which is the least, and even BIC is 757, which is the least among this possible. So probably I could see this particular distribution that I am looking at, it's much better to fit a gamma Pareto mixture distribution rather than going ahead with the gamma distribution alone. So we have improvised our model altogether, and probably graphically also we will try using the dense comp. Right, we'll try the dense comp, wherein the fourth model also let's add, which is called as gamma Pareto mixture. And here also along with y, let me put gampare. So that way I could see a better graph coming out, right? So this is how the gamma Pareto is coming out. So looks like there is a more appropriate fitting for the gamma Pareto distribution compared to the other three distributions as well. So that's how we can very well evaluate different kinds of distributions. You could see here slightly above this line is the gamma Pareto line, right? It is coming right from here like this, but you could see a slightly better fitment of the gamma Pareto line compared to a simple gamma distribution. There is only 11% probability that it is gamma, the remaining 89% is moving towards the Pareto. That's a mixture distribution that we have created. So these four, now I'll use the other evaluation mechanisms as well for a typical comparison. Now I have fitted all these distributions, right? I have got the shape parameter, the rate parameters, different parameters associated with each of these distributions. And if required, I can even add more and more distributions as well. Probably I can add a Burr distribution. I can try out combinations, mixtures of distribution, as long as I'm able to get a much increased number for the log likelihood, much decreased numbers for AIC as well as the BIC. Then the next important feature that we can look at in this context is the distribution function plot, which we have already seen the function that we can use. For the density function, we have used dense comp. For the distribution function, I can use CDF comp. All else remaining the same, right? There is nothing much for me to change. Only the last line here, instead of using a dense comp formula, I'll use a CDF comp. All else will be the same, right? Instead of using dense comp, I'll use CDF comp. The same four models I'm comparing using the CDF comp. So instead of plotting the density functions here, the cumulative distribution function is typically plotted for the fitted models as well as the actual data. Mm, okay, we require a Q function for it. For our fitted model, gamma Pareto, we require the Q function also for it. We have only defined the P function as well as the D function. Defining this, the P function, the P gamma Pareto, let me not define it with X, let me define it with the Q. Let me try that out. Let me not define this with X, let me define this with Q, and even these things, let me see whether this is the one that is causing the problem. CDF comp, yeah, I think I have to define it as Q when I am defining the P function instead of defining it as X. So this is where I could see that the CDF comp has worked, and this is how the cumulative distribution functions are coming out. So the actual is plotted in a black, the normal is looking more deviating, whereas I could see the Weibull and the gamma Pareto more or less being superimposed. So this is one way we could really assess which distributions are more and more closely fitting to a particular data and which of them are way away from it. Normal is looking like way away from it, right? Whereas it looks like Weibull, gamma, Pareto, more or less I am not able to make out too much of a difference by looking at the graph per se. Now, now that we have looked at histogram empirical densities, also we have looked at the distribution function. So just a quick look at the distribution. It is plotting the fitted distribution along with the empirical cumulative distribution function. So we have fitted the different distributions, compare the fitted densities that are carried out using fitted distribution using the CDF comp function, and in some cases I can simply fit only the tails also to get a much a better kind of a graph. I can also think of fitting only the tails part also. If we look at this function CDF comp, there is something to do with the tails alone. Not in this one, like. Okay, if we can try y limit, let me try this. So the same graph, if I set y limit only from, let's say, 0.95 to 1, the y limit I set only from 0.95 to 1, then I'm getting the tails. If I'm setting the y limit only between 0.95 to 1, I'm getting the tails where I could see which data is getting plotted more and more appropriately. Right? So you could see here, this is how the empirical data is getting plotted. The red ones are much away from this black. Then the one that is very closest to it looks like a gamma Pareto, then looks like gamma. Bible is slightly away from it, and even the normal is much away from it. So I can also get a plot of only the tails by changing the y limits. I will expand it looking at only the tails part, which can give me a much better representation of the whole graph, because in the full-fledged one I cannot really assess which one is closer and which one is farther off. So that's how we can improvise on the presentation of our graph as well, and even assessment of which distribution is more and more an appropriate fit to our data. Then moving on to the third aspect, which is used for assessing the adequacy of the model, we can look at the QQ plot or the PP plot, quantile plot, and the probability plots. So we are directly plotting the empirical distribution function. So on one axis we have theoretical distribution, the other axis we have empirical. So we are plotting the empirical against the fittest. Probably in the earlier two, the density, we had the empiricals plotted as histograms. Fitted is the kind of a line on this particular histogram. Whereas in case of cumulative also, that's the same thing. We have two different things. The empirical as well as the fitted, all of them are drawn on the same axis, seeing to what extent they are overlapping. Whereas here we have on one axis the theoretical value, on the other axis we have the empirical values. So if both of them are more or less, if empirical is more or less similar to that of fitted, we see that the line would be more and more, these two would form a kind of a straight line, because theoretical and empirical are looking more or less similar. It would be a kind of a smooth straight line. Whereas if it is more deviating, you find so many points like this, whereas the line is going like this. The quantities are computed based on the ranks of the different observations. We can use the PP comp as well as the QQ comp. So for this, first thing is we require, for our mixture distribution at least, we require the Q function also, because if I have to plot the QQ plot, I require the Q function also for my mixture distribution, which has to be a function of both Q as well as P. So we can use the PP comp and QQ comp functions. But of course, if I have my own mixture distribution, I have to write the Q function also. Till now, for gamma Pareto mixture distribution, we have only written the D function as well as the P function, but I have to write the Q function also for it. So let me tell you how we write the Q function for the gamma Pareto. So let's take Q gamma Pareto. So again the input, this will take the first input as P. So we'll Q gamma Pareto, I have to write it as a function. So P is one input to it. The same probability, how much it is a P, it's a gamma distribution, and how much it's a Pareto. So then we are giving the gamma distribution parameters and then the Pareto distribution parameters. Now the way we write this function is, we create one function L2, let's call it as a function which has to be minimized. We don't have a direct way of finding out the Q function. So that's where we are using an equation which we would be doing a minimization using the numerical methods kind of procedures. So L2 I am simply calling as a function of two things, Q as well as P. Q is the input that is going into a P gamma Pareto function, which is talking about the quantiles. So the way we compute this particular function L2 is we take it as p value, whatever is the input that is coming in for this particular quantile, p minus p gamma Pareto. So we'll bring in the cumulative distribution value that is coming from the p gamma Pareto, where q is the input to it. Then we have a probability. Then we have A, B, C, D as the parameters. So this is a very common mechanism that we can implement across. So this is the L2, which is actually the P, which is the actual quantile, minus the quantile, minus the cumulative distribution value that we are computing through the P gamma Pareto function. So that error, that is what actual minus the estimated. So I'm taking the square, calling it as a squared error. So we are applying across all the P values. So wherever all the kinds of P's that we are taking, we are separately applying this particular function. What is that function that we are applying? We are doing an optimize. We want to minimize the error. So that optimize, I am applying it across L2 for initially 0 to, let's say, different possible values 1000, wherein my p value equal to p. You can very well search for what is this optimized procedure. I'll get minimum of it, the minimum possible value associated with the same. So this is what is my q function associated with the q gamma Pareto distribution. So this, once I have the q function, I can very well go for my pp comp as well as the qq comp. Now if you typically search for pp comp, it is nothing but it is QQ comp is giving me theoretical quantiles against the empirical ones. PP comp is giving me theoretical probabilities against the empirical probabilities. So everything else is the same. So I can very well copy the same codes. The one that I have used for CDF comp, I can use the same for QQ comp as well. I'll get the quantiles, the list object, otherwise I should take it as the log scale, right? Instead of the original scale, cannot be coerced to double. So let me take it on a log scale. So let me call x log scale is equal to true, and let me also take the y log scale also to be true. Let's see, it could be the issue with the size. So I'm taking the x log scale as true as well as the y log scale as true. Still I am getting xy dot coordinates xy. List object cannot be coerced to double. Let me see if which one is having a problem out here. My function is having a problem here. I had to take the minimum. I have written it as I was getting omitted out here. So let me write my function again. L2 is a function of QP, or probably let me write the function right from Q gamma Pareto again. So let me write it as minimum. So let me check whether now the problem is resolved. Yeah. So one small spelling typo error out there. Now I am getting my QQ comp plot. So wherein I could see the line is coming out too weird, right? It's not coming anywhere. So the line is showing something like this. If I'm going with the log scale values for X and Y, this is how my line is coming out, which is looking pretty weird. Whereas if I don't go with the log scale, what is happening? Oh, even if so, it's looking pretty much weird. X log scale equal to true, Y log scale equal to true. Both of them I'm taking on the log scale. So the QQ plot is not coming out anywhere better for this. Now what about the PP plot? The same thing if I'm going with PP comp. Okay, PP comp is looking slightly better. Somehow the QQ comp is not working out well out here. So in this case also, if you look at the PP comp, the red one, which is a normal, is going way away out here, right? The normal is going way away. The one that is gamma Pareto and gamma are coming very close to this straight line. So we could still see that the gamma Pareto as well as the gamma are more and more appropriately fitting to this data compared to that of a normal distribution. So that's how I can take the help of QQ plots and the PP plots. So there is a no closed form formula for Q function of a mixture, right? So that's where I have to use a numerical optimization procedure. The way we are going with the numerical optimization procedure is we are going with for different possible values of P, we are trying to find out what is the probability that we can, what is the cumulative distribution value that we are getting from the applying the P function. So which is like an estimated quantile value. This is an actual. So this error, I want to make it as much minimum as possible. So that is what is the optimization that I have performed, and that is what is giving me the corresponding Q function for this particular distribution. So the quantiles and probabilities are plotted as points. Straight line is corresponding to the identity function. So this straight line says if the distribution, theoretical distribution, is same as that of the actuals, this entire set of points will lie along this line itself. The more and more closer the points are with respect to a particular line, the more and more appropriateness of the model or of the distribution to this particular data set. Now, any plot that we are doing on the distributed model, the fitted model, you will get all these four things. So, if I am doing a plot of normal, so these are what it is. The first one is empirical and theoretical densities, going with the normal distribution. This is the QQ plot. This is the PP plot. Sorry, this is the PP plot, and this is the CDF comp. Similarly, when you are going with each one of them, when you are going with plot of gamma, these are what are the definitions. We're not getting them all of them together. Similarly, if I am going with par gam par, these are the plots that are coming out with the gam pair. So this is one of the prime reasons. So here you could see the gam pair showcasing something like this altogether, whereas all others PP plot is looking much appropriate. So this is where the gam pair is losing out in the whole process. Whereas this is the one that is giving me the empirical and theoretical CDFs. So we could very well, so in GAM pair, there are so many NANs that are produced. That's the reason we are not getting the QQ plot properly for here, but probably yeah, you may have to go ahead and see where things have gone wrong. So you can directly use the plot method to get all four, but when we are using either PP comp or QQ comp or CDF comp or dense comp, we are trying to bring in multiple distributions, multiple fitted models into one single graph along with the empirical density distribution functions. So that makes our understanding of how closely the fitted models are appropriate to that of the actual data. Then, having looked at these three graphical kind of approaches for the same, we also have another approach which is a goodness of fit statistics and tests. So generally in case of continuous distributions, we have so many such kind of goodness of fit tests. We can take Kramer-Von Mises, CBM, Kolmogorov-Smirnov, KS, Anderson-Darling. So these could be the different kinds of methods, especially when we have talked about the maximizing the goodness of fit, MGE kind of a type when we have fitted the distribution. So this is nothing but maximization of the goodness of fit going with either of these three approaches. So in case of continuous data, we can use those three methods as the testing of the goodness of fit. Whereas in case of discrete distributions, I can use a chi-squared statistic, right? And any of the Akai-K information criteria and all are very much there. So when we are using the any kind of a function, fittest function that we are using, we are also looking at the GOF, which is talking of a goodness of fit parameter, especially when I am going with the maximization of the goodness estimate, which we have already considered when we are trying to fit the distribution. But yes, if I am fitting discrete distributions, like let's say for a particular data set I am fitting a Poisson distribution, binomial distribution, or some such kind of distributions, in that case if I have to really compare across the distributions, I have to rely on the chi-square distribution, right? I have to rely on the chi-square distribution. Whereas when I am going ahead with the continuous distributions itself, I can rely on CBM, Kolmogorov. Here in this case, this is the continuous distribution. So I could very well look at any one of these three and find out which one is having a much better GOF, right? I could try in case of CVM, KS, Anderson Darling. This is what we have tried when we have fitted the maximizing of the goodness of fit estimate. With different distributions, we can try that out, right? So for the gamma distribution, we can try out goodness of fit estimate based on each one of them, CVM, KS, AD, and based on them we will decide which model is more and more appropriately fitting to this particular data. And apart from that, we also have one more mechanism where we are simply trying to plot the skewness kurtosis graph. So selecting any distribution, depending on the type of application, we may have to focus more and more on the tails of the data. And we know skewness and kurtosis are two major measures which talk about the tails in the data. In a lot of places, in a lot of fields, actuarial sciences, in risk management, there's a lot of importance that we give to the tail of the distribution. Right? In some applications are exclusively focused towards the tail. In the broader world of risk management, including the actuarial sciences, we see that there's a lot of focus on the tail of the distribution. Along with that, we also focus on the first couple of moments, especially expected value of x, which is the mean, expected value of x squared. So we generally focus on these different aspects, but we could also look at the skewness and the kurtosis values also to focus more and more on the tails of the distribution. So let's say I'll take a simple case. I'll take a simple case where let me start looking at the tails of the distribution. So let me look at some different probabilities. So let me start right from point 0.9. I'll look at the tails. So I'll look at 95%, 0.95. I'll look at 97.5%, 0.975. And let me look at 0.99. And let me also look at 0.997 as well as 0.999. So I'm looking at different kinds of tails. For all the distributions, I want to look at the tails of each of these distributions. Right? So we can very well, in case of empirical, first let me look at the empirical part, which I can go with a quantile. I'll take the quantiles corresponding to each one of them. So from my original data x, from this original data x, I am looking at the probability equal to p. Let me see if I have got it or not. So corresponding, what is the 0.9 value, 0.95 value, I am trying to look at all of them from the empirical data. So let me see, the empirical values are, so the 90% is 1.79 million, 95% is 2.27 million, 2.74 million, and so on. These are my empirical values. Similarly, let me take my gamma values, or probably normal is my first, right? So let me call it my normal values, wherein I am taking the quantile, my what is the name of the model? The fitted model is GAM, and I am also taking the probability equal to P. So we are going with the quantile, and I am getting the quantiles associated with this. So you could see that the norm is giving me, so the 90% value for the norm is working out to 1.89, whereas if it has gone to 99.9, the value is 4.25, going with the normal. Oh, sorry, why did I take GAM? I should have taken norm. This is for the normal distribution. So the norm values for me are something like this, 1.88 to 3.11 itself. But when I am looking at GAM, these same quantiles in case of GAM are 1.89 to 4.25. Similarly, when I go with Weibull, these same quantiles, so these are the extremes. So I am looking at the tails for all of them. So when I am going with Weibull, it is going 90% is starting at 1.91, but it's going only up to 3.8, whereas my empirical 99.9 has actually gone up to 5.7. So similarly, whereas the gamma has actually gone up to 4.25, slightly approaching, but 5.7 is too far. So that's where the tail is not getting captured even by my gamma. But let's see gam pair. In case of gam pair, this is the distribution that I have created. The gam pair is working out. It looks like there is some problem with the Q distribution that I have created. So the Q actually needs to be improved, right? I think there is some problem with the Q function that I have created. Q gamma Pareto. Let me recreate it once. Q gamma Pareto. I'm taking it as a function of P comma probability comma A comma B comma C comma D, wherein I'm starting it off. L2 is a function that I'm considering. This is a function of Q comma P, where I'm considering P minus, which is the actual, P gamma Pareto. I'm taking P gamma Pareto as a function. Q is an input to it. Prob is another input to it. Then A comma B comma C comma D are the parameters of gamma as well as the Pareto distribution. I want to minimize this particular value, so I am taking the square of it. Then I am separately applying the same across all the P's, right, where I am considering a function of P, where I am doing optimizing L2, considering different possible values from 0 to 1000, setting P equal to P, and for this I am getting the minimum, and I am closing this. So now let me see whether I am getting the Q gam pair correct or not. So something is going wrong somewhere. So let me just check for a mixture distribution why it is going wrong, but otherwise you got the concept for the existing distribution, so we don't need to bother much in terms of existing distributions. Somewhere with respect to the created distribution, a small mistake is coming out in terms of the definition of the Q function for the same, right? So that's one way. Similarly, you can go ahead in terms of computing the first and second quantiles, right? So first and second moments, the initial moments also can very well be computed for each one of them. So you could very well go in case of empirical. So we can first of all we have looked at the tail of the distribution. Now we will try to compute the first few moments. So let's say if I want to go for gamma, the first few moments associated with the gamma distribution. I'll go with m gamma, which is my moments. I'll get the moments, the first order, the second order. So I'll take the first order moment associated with the gamma distribution. I need the parameters of the gamma distribution. So I can directly take GAM. GAM is my fitted distribution. So within this, I can take the first list, first element. That is what is my estimate. That is what is my shape parameter. And the rate parameter is the second one of the first list. So either if you remember it, fair enough. Otherwise, this is one way you can trace the shape and the rate parameters of gamma distribution. So the m gamma is coming out to, the mean is 1.01 for the gamma distribution. Similarly, you can very well go with the second order, which is expected value of x squared. So this is expected value of x squared, this is expected value of x. Similarly, now let me go with the normal distribution, m norm of, so instead of GAM, let me take NOR of the first one and NOR of the second. I know the mean and the standard deviation of them, so we don't need to really compute. The mean is whatever is the parameter that we have got. So this is the variance, which is the parameter that we have got. Expected value of x squared is this one, and the expected value of x is 1.01, even going with this kind of a process. So similarly, I can try out all the possibilities, right? Will it come out if I have to go with gamma Pareto? I have to take the coefficient, the shape parameter in case of a mixture distribution. If I have to take it, it is like I have to take probability times the moment of the first one, the gamma distribution, plus 1 minus probability times the moment of the second. So let me take GAM pair. Let me get the values of GAM pair. So these are the values of GAM pair. So this is where I will now take, if I have to really compute, I'll take the probability. If I want the mean of this particular distribution, it is nothing but I'm considering this particular probability multiplied by m gamma associated. So this is the probability, right? So let me take it as by 100 multiplied by m gamma of the first order, and the a value is this much and the b value is this much. So this is the first part, plus 1 minus of this value divided by 100 multiplied by m Pareto of 1 comma the order 1, and the parameters are 117 here, and the next parameter is 50.23. So this is how we compute the moments associated with the mixture distribution. So this is the first moment associated with the mixture distribution, and if I have to go with the second moment, all I have to change it here. So expected value of x squared for this is this much. So expected value of x is this much, expected value of x squared is this much, and you can very well go ahead with any kind of an order computation. So this is one more thing that we can look at while we are computing the graph that is associated. So we can very well compute the mean, which is the first moment, the variance, the second moment, and even the tail of the distribution to really understand how my distribution is typically looking like. And along with that, I could also go ahead in terms of getting an estimates of the skewness as well as the kurtosis. I can go with disk dist. Disk dist is a function. So let me see what is disk dist. Computes the descriptive parameters of an empirical distribution. So for an empirical distribution, it computes the descriptive parameters, non-censored data, and based on that it can also provide a skewness kurtosis plot. So if I give the data to it, especially with the empirical distribution, I can get that plot, right? I can give the data. So if it is by default, it is not a discrete data, it's a continuous data. By default, the bootstrapped value is null. So if not null, boot values of skewness and kurtosis are plotted from the bootstrap samples of the data. Boot must be fixed. In the case it should be above 10. So if I want even the graph values to be plotted, I'll not set it equal to null, I'll set it to some number, let's say 100. So 100 different values would be plotted for the bootstrapped value. The method, it is unbiased, and all other things I think it should be fair enough. So the boot color is by default in an orange color. So we can very well go with desk dist kind of a function out here. So we'll say desk dist, wherein I have to give me the data here, which is the x in this case, and discrete is false. Boot, let me set it equal to 100. So it is actually giving me different kinds of distributions out here, right? It is giving me different theoretical distributions. The star is talking about a normal distribution. The triangle is a uniform distribution. The exponential, so you could see plus is a logistic, the one in a cross. So we have the observation, bootstrapped values are coming out here. We get the estimated kurtosis value for this, which is coming out to around 2.57. Estimated skewness, it's a positively skewed kind of a data. We are having estimated kurtosis for it, which is lying in a very high range. So we can very well go ahead with the looking at this particular graph called as Cullen and Frey graph, which actually plots the square of the skewness versus the kurtosis. So this is what is for our observed value. These are all the bootstrapped values. And when I am looking at the theoretical distribution, these are the different distributions which are going like this. And you could also see the light dotted lines are the log normal distribution. So you could see that it is more and more closer to the log normal distribution compared to a gamma distribution. This is the line of fitment for a gamma distribution. This is the line of fitment that is coming for a log normal distribution. So there is a possibility that I should have considered a log normal distribution also, because the skewness and the kurtosis are typically resembling this particular plot. And the fit analysis can be completed by looking at the uncertainty of the parameter estimate with this bootstrap analysis. So I can use the boot dist function here. right, instead of desk dist. So let's look at this function called boot dist. Use parametric or non-parametric bootstrap resampling in order to simulate the uncertainty in the parameters of the distribution fitted to non-censored data. So we are talking about different kinds of stuff. So we can take an object of the fit distribution. We'll take a boot dist function. We'll take for the normal distribution. We'll take for gamma distribution. We'll take for Weibull distribution. The booting method, I can take it as default, parametric, number of iterations, everything. Let's make it default. The only thing is I would give the input as the booted distribution. That's it. Right? I'll only give the boot dist. Let's see this. I'll give boot dist NOR. NOR is my normally distributed model, fit distribution model. So this is how the parameter values are coming out. Using this boot dist function, it says it has tried different kinds of combinations. You could see that the parameters are typically 1.0 to 0.99. So this is the kind of range that they are varying. Standard deviations are also in this typical range. Right, so I could get a combination of the standard deviations and by going with different again within this we have different kinds of parallel methods. Either I could have no or snow or multi-core. So these are the different kinds of methods, but what we will get in a boot dist typically is the different possible values of my parameters. So if I go with boot dist associated with gamma, these are the different parameter values that are coming out. Right, so you could see that they are varying anywhere between 2.16 to 2.6, the shape parameter, and these are the kind of range of values that are associated with the rate parameter. Can I get the same for my mixture distribution as well? No, I need to define the R gamma Pareto also. Yes, we may have to look at for a mixture distribution. If I have to define, it's better that I define all four of them. We have defined the P, we have defined the D function for it, straightforward, easy to define. We have also defined the P function. Q somewhere is going wrong for me, but we can very well refer to the literature regarding that. We can create our own mixture distribution, both the Q as well as R. If we are creating, we can very well do all this process on the mixture distributions as well. Similarly, for my Weibull distribution, I am getting so from here it can very well be inferred that looking at the actual plot versus the distribution, log normal is coming much closer to it in terms of the skewness and kurtosis. So I should try the log normal distribution compared to the other distributions from here. The gamma distribution is coming slightly out here, whereas the log normal is where there's a lot of centering that is happening. So it's better that I try that distribution as well. So that is what I wanted to cover as a part of this session, where once we have fitted the model to a particular data, how can I really evaluate the goodness of fit of those models using histograms, empirical densities, distribution functions, QQ plot, PP plots, goodness of fit statistics, as well as the skewness kurtosis graphs. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given, as well as you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.